In the previous video, we talked about winds and how winds are produced. And you saw this picture, which was an idealized view of how the convection currents are actually moving in the atmosphere. And as it would appear in this picture, these, these convection currents are perpendicular to the equator. In real life, that's not actually how they are. And the reason for that is this thing called the Coriolis effect. And the Coriolis effect can be confusing, but what this basically is things that are traveling in a straight line from like the North Pole to the equator look like they are traveling in curved paths when actually they are traveling in straight paths. And you may be thinking, what, huh? I don't understand. So let me kind of use an analogy, and then I will explain this again, and then one of your assignments for this lesson is that you're going to find some sort of video or animation that helps you to understand this idea better. But right now, I want you to imagine that you have a string in your hand, and at the end of that string or rope, you have a ball. All right, so if this is your hand right here, okay, and you're clutching onto a ball, okay, or a string that has a ball at the end. So here's our ball, okay? And you're going to spin that ball over your head, okay? So that ball travels in a circle, okay? So it's going around in a circle around your head, okay? Traveling this way. I want you to think of this rope, okay, and this ball kind of like as the Earth. So your hand right here is like the North Pole, okay? We'll abbreviate that as NP. And then this ball right here is the equator, right? And the Earth is spinning, okay, so it's going in a circle. And if you look at different points along this string, okay, you'll notice that they will be traveling at different speeds. So if you look at a point that's up here closer to your hand or to the North Pole, in one rotation, okay, this point on this string only has to travel this far to complete one rotation. Whereas the ball that's all the way down here, okay, in order for that to complete one rotation, it has to go all the way around. It has to travel much farther to complete one rotation. So the ball out here, down here on this string, is actually going to be traveling at a faster speed than the point that is closer up here towards the North Pole or towards your hand, because they have to cover the same amount of distance or a different amount of distance in the same time. And so the one that's up close to your hand or to the North Pole doesn't have to travel as fast to complete one rotation, whereas points out at the equator or closer to the end of the string with the ball have to travel much faster in order to complete one rotation in the same amount of time. So basically what this means is that if we shoot off like a rocket or a weather balloon from the North Pole and we're aiming it down here towards the equator, what happens is these points at the equator are moving much more quickly than the points up here at the North Pole. And so when we shoot this rocket off or shoot this weather balloon off, it's going to, that rocket or weather balloon is going to travel in a straight line, but the Earth that's underneath it, as it moves towards the equator, is going to move even faster. It's going to start moving faster. So as that rocket moves and goes in a straight line, the Earth underneath moves faster, and it looks like that rocket travels in a curved path, when actually it's going straight. So if you're up here at the North Pole, okay, and you're shooting a rocket down here towards the equator, okay, these points down here are going to be going much faster than these points up here, and so the rocket is going to travel in a straight line, but it's going to look like it travels in a curved path because it's going to, the Earth underneath is moving faster. All right, so here's a couple other pictures to try and help you see this. All right, so here's our weather balloon. That's where we're aiming, okay? So this is, again, where we want to hit. Because this is spinning, okay, when we shoot off that weather balloon, the weather balloon is actually going to land over here rather than here because the Earth moves faster underneath the balloon as it gets closer to the equator. Because of this, The Coriolis effect actually causes the direction of the convection currents, and therefore the winds, to be curved relative to the Earth. So rather than being perpendicular to the equator, they're curved. The winds are curved relative to the equator because of this Coriolis effect. So it actually bends the direction of the winds. This picture here is here to help you see kind of more of a realistic view of what the winds look like on Earth. So it's not that nice, pretty 3 convection currents per equator or per hemisphere. The wind patterns are actually much more complicated because of this Coriolis effect and the rotation of the Earth.